So thank you very much, Sam. And my name is Liam O'Brien. I'm a professor at Carleton University, which is in Ottawa, Canada, Canada's capital. And today I'm going to talk about how engineers think about building occupants. And I modified the title slightly to add 12 myths because the way this is structured is that I've populated 12 myths, the top 12 myths I could think of from the literature or things I've heard or things that have emerged otherwise from our research. And then I try to address them briefly. And I only have about 35 minutes, so it's pretty brief. But if you have questions about specific examples I provided, I'll be very happy to answer them. Um, so before I get into the meat of this talk, I just wanted to note what Sam was saying. I'm one of four people that leads a big project called the Human-Centric Buildings for a Changing Climate. And this is a pretty unique project in that it's under the International Energy Agency Technology Collaborative Program, but it's under two different TCPs. So it's under the EBC, and I note Melly Stylianou, the chair of that, is here. And it's also under the user-centered energy systems, because we really feel this topic needs to go under both of those. Um, so just a little bit of background. I've written three books, and you can sort of see the trajectory of the books, but they've all been under the IEA TCP programs, starting with a little bit more general, how do you design net zero energy buildings? In a previous project called NX66, we looked at research methods to understand people in buildings. And this took a very interdisciplinary approach, looking at everything from sensors and technology to the ethics of collecting data from people. Most recently, we published a book that's open access. So it's free to read and download. And it's called Occupant-Centric Simulation-Aided Building Design. And this tries to take, I would say, advanced practitioners and researchers through the whole design process. Everything from understanding people to how do you design for people? How do you use simulation to design better buildings? Um, so the project that we currently have, which we've called the HCB network, just because it's a little bit shorter, um, is focused broadly on individual behavior and well-being and comfort, but also at the community level. And at the community level, we're looking at topics like equity and sufficiency. Um, we're looking at the whole building life cycle as well, everything from design, operations, and redesign. So we've structured our project accordingly. The project has over 100 researchers from over 20 countries and 10 disciplines. And we're really proud of this fact because we feel that this is not a topic that engineers or even architects alone can handle. Um, and I'll note that we're trying to improve involvement from the global south and other areas where it would be typically hard to afford to travel every 6 months, as these projects usually have. And so we have hybrid meetings, and one of our next meetings will actually be going to the global south. So with that said, I want to dive into this topic. Um, and I'm not going to talk about my PhD other than to kind of give my origin story of why I went from being purely an engineer to recognizing the importance of people. So my PhD project involved developing a design tool that allowed designers to rapidly change different parameters for a house and understand the energy implications of that. But at the time, I was really frustrated because things like the set point and lighting and equipment that people used um, tended to have a much bigger impact on predicted performance than things like insulation and windows. Um, and at the time, that was frustrating, and now I appreciate that this opens up a huge area of research. And it's particularly notable that as our buildings become more efficient, we've sort of mastered envelopes and to some extent HVAC. Our lighting's never been more efficient. The role of the occupants in relative terms is much more significant. And so that's one of the reasons we've seen an explosion in growth in this research area. Back in my PhD, I had a case study building an award-winning house, and I think it was very successful. But it was also eye-opening to me because the book, sorry, the house is sort of textbook perfect. It has large south-facing windows, thermal mass, a PV and thermal roof, a ground source heat pump, which was fairly novel at the time. So from an engineering perspective, this house is near perfect. And I still think it's a great house, but it was eye-opening to me when I talked to the occupants who moved into it, and I looked at some of the things they did. And I'll just highlight a few things. One of the things they did was to cover the thermally massive floor, which of course has a very important role to store solar energy and release it so that the space doesn't overheat. Well, the occupants covered most of this floor with a carpet and furniture, which renders it much less effective. On the other hand, if you think about the perspective of the occupants, they didn't want a cold floor that they'd come down to, in the morning with bare feet. Um, the north side of the house had almost no windows, and surprise, surprise, the occupants installed a lot of lighting, and it was not very energy efficient. Had the designers anticipated this situation, they could have at least, if they didn't put windows, they could have put in energy efficient lighting. But the most surprising thing that they did was to put a very high powered 5 kilowatt electric heater in the garage because the designers assumed, understandably, that the garage would just be used for storing a car, so you don't need to heat it, probably. The occupants decided they wanted to use the space for other things like woodworking. And so it turned out that this small heater used a third as much heating energy as the whole house. Again, I think it comes down to the designers, if they had anticipated the way people actually behave, could have incorporated these things into design. So this talk is somewhat based on this paper we published 5 years ago that looked at the state of the art of occupants and then research at the time in 2020. And we came up with a list of myths. And so the list of myths I'm presenting here are from there as well as some new ones. But I should note, I'm only one engineer. I can't speak on behalf of all engineers, and I will admittedly make some exaggerations just to make a point. So please don't assume that I speak for all engineers. But at the same time, I think my points are quite reasonable, if I may say so. So the first myth is that occupants are like weather, they're just a boundary condition. And a translation of this is design doesn't affect behavior. So that's our first myth of the day. People are not a boundary condition. In the case of weather, if we're doing modeling or simulation or even measurement of real performance, the weather affects the building, but the building doesn't really affect the weather. Of course, there's things like climate change. I'm not denying that. What I'm saying is that we don't usually design our buildings thinking that we're going to change the local weather, except for some nuanced cases like microclimates. In contrast, there's a two-way relationship between people and buildings. If people are not comfortable, for example, they will actively change the buildings. So it's simply not the same situation. Um, but unfortunately, this idea is often reinforced. So this is a figure from the ASHRAE Advanced Energy Design Guide, which I think is fantastic because it tries to show in a single diagram all of the different building systems and the relationships between them and the heat flows. I mean, to look at this already is a huge upgrade from what's typically done, where we have kind of siloed design. But I'll note that sure enough, the occupants are in the corner, and they're merely, according to this, a source of sensible and latent heat gains, and also things like odor and CO2. Um, so this is reinforcing the idea that occupants are just a source of noise. Um, Building codes also tend to do this. We've done a huge review of building codes for our previous project, and we found a lot of building codes won't even acknowledge occupants. They they have very indirect ways of saying people or users or occupants without actually saying it. It's quite remarkable. And on the one hand, it's understandable. So for example, ASHRAE 90.1, which many building codes are based on, says in no case shall schedules differ where controls are manual. Um, this is code for you can't assume good things about occupants. And the Canadian Code for Commercial Buildings says something very similar. Basically, you can make some assumptions, but you cannot assume optimistic things about people. Um, and this may be fair because it's obviously subject to lots of sort of cheating if we make good assumptions about people, when certainly there's uncertainty. But we're also taking the license away from designers to try to design better buildings for people. So what I'm advocating for is going from this model that says occupants are just a source of noise on buildings, and then, that results in some performance, whether it's energy or emissions or comfort, to more of a two-way diagram that says buildings affect people, people affect buildings. And there's all sorts of intermediate steps in there, like indoor environmental quality, interfaces, interfaces that nudge people, etc. More on that later. But just as one illustrative example for how design affects people, because I really believe a lot of designers, or especially engineers, don't think that you can affect behavior. I did a case study where we looked at two residential buildings in Ottawa, and in brief, the one with big windows um, has occupants that close their shades or their curtains a lot more than the one with small windows. And so much so that effectively the open area where there isn't obstruction from shade or walls is very similar. So this, to me, is good evidence that you can affect behavior through design. And so the question here would be, why are we giving people these huge windows when they just keep them closed for privacy, glare, overheating, etc.? I'll also note something we're looking at in our new project is nudging. And here's just a quick example of nudging. So a study out of California found that if you signal people and you tell them it's good to open the windows now, or it's, not wise to open the windows now, then they will feel empowered and sort of validated to open the windows. Because the risk on the left, what I'm trying to illustrate, is that oftentimes we're afraid to behave and improve our comfort in buildings, because everyone will stare at us, especially if we adjust things like lights. It's going to attract attention, and so we might decide to cope and suffer rather than improve our comfort. Some other examples of nudging: providing nice stairwells, providing a slide even as an alternative to elevators, or messaging that encourages the more energy efficient behavior. Second myth, occupants are merely recipients of the indoor environmental conditions, and do not actively respond to improve these conditions for their benefit. I think this is also a myth. Um, and here's a nice example, just showing the sort of interaction between building operator or manager or owner who doesn't want the occupants to have control. Um, but sure enough, the occupants had the last laugh because they tricked the thermostat into thinking conditions are much colder. Um, Here's another condition where the assumption from the designers or operators was we know what's best for the occupants. Well, this is a case where the occupant who has a PhD or has a PhD now outsmarted the lighting controls. So what you're looking at here is a drinking bird that tricks the motion sensor to keep the lights on. But it was completely legitimate why the occupant didn't want the lights to turn off. He was around the corner from the motion sensor, so the lights were turning off prematurely. Next myth: controlling buildings based on average occupants is adequate. There's just no such thing as an average occupant, or there is in the mind of engineers, but in reality, they're very diverse. Just one example: this is a study from 2014 that tried to come up with the preferred lighting level. I think it was in offices, and the graph shows basically the percent of people that preferred these various conditions, the units in lux, and um, the engineering approach to this is, well, we need to come up with one value that will satisfy most or all. And so we just need to choose one value because you can't really have a standard that has ranges, admittedly. So we need to pick that one value. The problem with this is that anyone that prefers less than that value would have saved energy if we gave them control. And the people that would prefer more, perhaps for legitimate reasons, like their eyesight isn't good, or they're doing an activity like drawing that requires a lot of light, those people would be dissatisfied. So to assume that everyone is like the average is quite problematic, um, and not just for discomfort, but also for energy savings. This is one of my favorites. Occupant diversity equals uncertainty equal bad. So engineers do not like uncertainty because uncertainty is very expensive. If there's uncertainty, we need to over-design and take conservative approaches because we don't want bridges to break, cooling systems to be undersized, etc. But I'd like to argue that actually diversity is an excellent thing, and I think we know this, we just forget about it. And I'm not talking about the usual kind of diversity, I'm talking more about, well, I'll show you. Um, so here's just one illustrative example. This is a graph showing water use during a hockey game in Canada. Um, and you could see, like clockwork, at the end of the period where there's the break, all the spectators go and use the washroom, and that's why we see these huge peaks. Um, Peaks are bad. Peaks mean that we need a system that can achieve the peaks. And if the peaks are really high compared to the average, then our infrastructure or our building needs to be able to achieve those, even if it's oversized for the majority of the time. In a similar case, there was a recent traffic jam in China at the end of a national holiday, and apparently this is 36 lanes of traffic. Well, again, peaks are really expensive because we had to have 36 lanes on our road. If we had average traffic all the time, we could get away with just a couple of lanes. Um, so in a more grounded example, I've done some research looking at um, how diversity of office workers in terms of schedules can also be really good. Because if we design our office buildings so that on the worst case, the busiest hour of the year, there's enough desks, then we're going to end up with a lot of extra desks, especially in a hoteling situation where people do not sit at the same desk every day. Next myth. Occupants do not understand how buildings work and will often waste energy relative to design intent. So engineers often will blame occupants, and in some cases that's legitimate. But I'd like to say that that's generally a myth, and I don't think occupants willingly or intentionally waste energy. It's more that they do things that make sense to them, and if that wastes energy, well, maybe we should look at the designer. I'll just give one quick example. My PhD student, for his very first paper, my first student, first paper, noticed that his friend was keeping his apartment really warm, and my student was not keeping it warm. And he asked, how can you afford to keep it so warm? And his friend said, well, I don't pay for the heating. It's just included in rent as a fixed fee. And so my student measured the temperature in 20 what we call bulk metered units. So apartments where heating is included, and 20 where they pay for exactly how much they use. And what he observed over the whole heating season is that tenants who paid for their heating kept their apartment on average about 2 degrees colder than their counterparts. And so to me, this is an excellent example of how people know how to save energy. If you charge them or have other incentives, they know how to save energy. And he also found that the people who pay were much more diligent about keeping schedules. So, for example, turning down the set point when they were off at work. Next myth, automating building systems minimizes the negative impact that occupants have on buildings. Engineers like to automate everything because they're very comfortable with things like programming and logic. They're not so comfortable with the complexity of humans. So I'll give one example. This is a building at Carleton University, and it's extremely well daylit, which is very relevant here. So the outside of the building is surrounded in professor offices, and the windows are massive, arguably oversized. Um, what we noticed when we did a post-occupancy evaluation here, and it was very surprising, is that the occupants or many of the occupants covered their motion sensors with tape or paper or even plants. And this is quite different than what I showed in the previous example. And we asked them why, and they said, we don't like it when the lights turn on automatically when we walk into our office, because the default controls at the time seem to be that the lights turn on automatically when they detect motion. And this is actually against the code now, which I'm glad to say, um, because it doesn't make much sense. What we discovered is that it's very easy to change the controls. And so after, so we left the sort of bad controls for a year. We made an intervention where we changed it so that the lights only turn on if they turn on the light. This saved 95% on energy use. And so it's not a lot in absolute terms, but in relative terms, it's quite amazing. And so we have a situation where the people didn't like the automation system, and that automation system was actually taking more energy. So the result was happier people who are using less energy. A big open question for designers, not just engineers, is how much should we automate our buildings? Engineers will say, automate like crazy, use AI, we can predict everything, because engineers also have that level of ego oftentimes. Um, But other disciplines might say, actually, we should give a lot of control to people because we know, for example, that people who have more control will be more tolerant of a wider range of conditions. Well, a wider range of conditions translates usually to energy savings. Next myth, providing ideal indoor environmental conditions can replace the need for giving occupants control. And this is quite related to the previous one. Um, But I'll just give the example again at Carleton. We did a field study. We went into about 200 professor and staff offices and we asked them many questions. One of the questions was, have you plugged in anything to improve your comfort? And to my huge surprise, about 50% of occupants had plugged in a space heater, a fan, a dehumidifier, an air cleaner, etc. And the most problematic situation was where, and there was quite a few of these, they'd plugged in a space heater in the cooling season and they were using it because the building was being overcooled. Um, and so while this is a pretty energy inefficient way to achieve it, it tells us that trying to provide comfort centrally is really challenging to the extent that I would argue it's basically impossible between the number of circumstances and contexts and also the diversity of people's preferences. It's really hard to achieve comfort with a single set point on an entire university campus. Some of the solutions to this that we're looking at a little bit, but other IEA, EBC projects are looking at is personal comfort systems that say, we acknowledge you cannot centrally and perfectly control the environment. Um, Not only that, but just conceptually, it doesn't make sense to condition buildings. It makes sense to condition people. And so these technologies look at two benefits. One, heating and cooling and lighting people or their direct vicinity, um, but also giving them individualized control. It just makes so much sense. Um, but I'll give another example where there was some effort to incorporate comfort in design. This is the NREL RSF building in Colorado. Um, and what they did, I think, is quite brilliant, where they designed the interior, for example, to avoid any direct glare. So the bottom half of the windows um, allows daylight through and views. The top half have these light louvers, which reflect light up onto the ceiling, which is not only good for getting daylight deep into the space, but it also prevents um, glare for the people sitting at the desks because any light that would hit the occupants is reflected up onto the ceiling before it can hit the occupants. Next myth, occupants function on regular clockwork-like schedules. And again, this is reinforced by the building codes, and it's kind of understandable why, because we do need some sort of reasonable assumptions. But at the same time, it's not very realistic. Um, and so there's many examples comparing occupancy, so the presence of people, and behavior to standards. But inevitably, they almost always show that the assumptions are are that occupants or occupancy is high, hours are long, etc. Um, Similar things for lighting. This is work that's a couple of decades old from Christoph Reinhardt when he was a PhD student. But it's showing for 10 individuals the probability that they turn on their light when they arrive in their office. And we can notice a few things here. And I shaded this yellow area to say this is what engineers might assume. People want 300 lux or 500 lux. So what we should do, if the engineer would think, is if the light's below that, turn on the light. It's kind of like the way a robot would behave. The reality is we can see the people are diverse. These lines are very different forms. Even if you don't follow the graph, you can appreciate there's huge diversity. And um, the conditions that would trigger people to turn on the lights are much lower than the standards would indicate. In other words, people are happy with much lower light levels from daylight, for instance, than what the standards would indicate. Um, Speaking of occupancy schedules, we did a case study where we talked to three professionals that were working on the same building in Toronto, the architect, the energy modeler, and the mechanical engineer. And we asked them what assumptions they made about people and also the lighting and the equipment, which are all kind of related to the occupants. Um, and we found huge diversity between these three parties. And I don't think that's necessarily a problem or surprising. Like the mechanical engineer's job is to make sure the cooling equipment is sized big enough. So of course they're going to have higher assumptions, I think, because they need to make quite conservative assumptions. Um, I think the problematic thing is how this translates into design, because what we found is that the different assumptions lead to very different optimal design decisions. And while the assumptions are sort of inconsequential in their own right, the design is something that we're stuck with for the rest of the building's life. Next myth, the best way to deal with uncertain occupancy is to make conservative worst case assumptions. I think this is also a myth, and this relates a bit to the diversity. Diversity is a good thing. If everyone behaved in the worst possible way, then yes, we should make conservative assumptions. But I don't think it's reasonable to assume everyone behaves in the worst possible way. Um, so I apologize. This is probably the most technical slide here, but I'll keep it high level. I did a study where I measured lighting and plug loads, so sort of equipment use like computers in many different offices. And then I sampled that repeatedly to understand what is the probability that we truly have a building with those worst case conditions. Um, and what I found is that there's a big gap between what the building codes and standards will tell you to assume and those very worst case scenarios. In other words, if we follow building codes and standards and those assumptions related to people, it will tend to lead to oversized equipment. And this is just one example. Next myth, indoor environmental quality, or IEQ, is a purely physiological phenomenon that we can accurately predict from first principles in engineering. So engineers are very comfortable with things like heat balances and this Wenger thermal comfort model, which I describe as a blob, because it's basically engineers speak. It treats the human as a blob for which we can draw things like boundary conditions and arrows indicating heat flows. And the Wenger model is based on the premise that if all of the heat generated from our metabolic rates, basically our calorie burn, equals the heat loss from convection, so from like airflow near our bodies and radiation and sweating, and this is reduced by clothing. If all the heat gains and heat loss is balanced, then someone should be comfortable. And I'm simplifying it a bit. The problem with this is that it ignores things like people's personality and preferences and psychology and previous experiences and tolerances and things like that. So about 25 years ago, we developed, not me, but the research world developed something called the adaptive thermal comfort model, which says we can ignore most of that heat balance. While there's some truth to it, there's also a lot of other considerations like the psychology and behavior of people. What this model says is that the only thing we need to do to predict whether someone will be comfortable is to know what the temperature is outside. And this is a really uncomfortable thing for engineers because why does the outdoor temperature matter? The outdoor temperature was not in the equation or in the model I showed on the previous slide. Why does it matter? Things like people get accustomed to certain temperatures, they dress appropriately, they can open the window strategically to let in cool air or warm air. Um, and so this is fairly profound for engineers. And unfortunately, it hasn't been adopted as much as I'd like. In another example from Finland, um, this study called a few thousand people and it said, what's the satisfaction with or what's your satisfaction with room temperature in these various places? In your house, or in your apartment, in your private office, in your open plan office, etc. And I don't want to go through every result, but the trend is really clear. It's downward, and from left to right goes from a single family house where you have ultimate control over the temperature, you know the people you live with, so you're not uncomfortable negotiating or maybe fighting with them, etc. And on the other extreme, we have open plan offices. The uh, there might be one thermostat if we're lucky, and we can't control clothing level. I mean, unless we want to get fired potentially. Certainly not to the level that would lead to ultimate control over comfort. And interestingly, they found the fact that the HVAC is opaque, it's behind the ceiling, you can't see what's going on, means that you don't understand it and you're less likely to be satisfied. Next myth, the four domains of IEQ, so indoor air quality and thermal, visual, and acoustic comfort, are independent from each other and have equal roles in occupant comfort and well-being. This could be a whole talk in itself. Um, but in brief, these are the four domains of indoor environmental quality. And one of the issues among many is that usually there's one professional designated to addressing each of these. So, for example, the mechanical engineers often take care of the indoor air quality through ventilation. The architects also look at things like material selection. The architects might look at visual comfort from a daylighting perspective. Maybe electrical engineers are looking at lighting. Um, but there isn't usually a professional looking at all of these simultaneously. And so often there's trade-offs between them where we try to improve one and we forget that that's going to affect the others, often negatively. The other thing is that engineers want to weight these equally and say, okay, each one is worth a quarter or something of the total score. The reality is that if we're blinded or if temperatures are really warm, like 30 or 40 degrees, probably the others are not going to be that important. So it's this the idea of weighting them just doesn't work well in reality. And I'll give an example. Same building I showed before. Um, One of the challenges with sustainable or green buildings, whatever you want to call them, is that a lot of the things we do to improve things like natural ventilation and daylight penetration, so you can see low partitions here, are also really good at transmitting noise. So I think this is an example where they did a really good job. They put in a lot of soft elements like a carpet, acoustic tiles on the ceiling, which is otherwise quite hard. It's metallic and reflective. And some booths where you can do things like fire people that you wouldn't want to do in an open plan office. And the last myth, energy efficiency and renewables are the only way to achieve energy savings. So engineers love technology and design that can sort of force things to happen that are predictable. Um, but in our work, we like to think of another aspect, and one of those is called sufficiency. So just a little background before I go into what sufficiency is. This is a graph of Canadian housing stock data from 1990 to 2015. And I'm really proud, and I think our government officials and building codes and developers, designers, etc., should be proud that we achieved about a 50% drop, almost, or 40% drop in energy efficiency, or sorry, in energy use, which is a result of efficiency. Um, and this is particularly impressive when you consider that we're stuck with this building stock that was built way before 1990, before building energy codes existed. But the problem is, in that same time, our homes got bigger, and our households, in other words, number of people per home, got smaller. So the result is the energy use or emissions per person did not drop that much. It dropped about half as much as energy use. And so there's a concept called sufficiency, which is, if you will, the sort of third pillar in addition to energy efficiency and renewables, that says we probably don't need as much floor area, and we can achieve that through things like sharing spaces, improving efficiency, home swapping is something that maybe the Airbnb model sought to do before it got very commercialized. The idea that if you go on vacation, someone could use your home, and so we don't actually need as much floor area for the global building stock. Um, so this figure's a little bit complicated, but in essence, the area on the graph represents the energy or emissions per person. Conventionally, we focus so much on energy use or emissions per floor area that we forget that if those floor areas are getting bigger, we may not be ahead. And so my fear is that at the same time we're seeing energy efficiency and renewable energy improve things, which they have a lot. If our floor area gets bigger, we're just skewing this rectangle the same way. But it's really about the area. It's about how much emissions or energy use per person, and then multiply that by the number of people. Um, Sufficiency looks at reducing floor area, but again, this shouldn't be seen as suffering or poverty. It's more about improving utilization and even providing more amenities that individuals might not be able to afford, like a community swimming pool or community pizza oven or that sort of thing that individuals typically would not be able to afford on their own. The other thing our project is looking at is resilience at the community level, recognizing that resilience is not just about battery backups or diesel backups or well-insulated buildings. It's also about things like relationships with neighbors, so that if someone's sick, we can rely on local neighbors for healthcare, for food, for exchanging or trading goods and services and tools, etc. So I won't dwell on this diagram, but it basically says if we have streets with a lot of traffic, then people are much less likely to know their neighbors or to have friends in the neighborhood. Um, and so it's saying make our streets quieter and you'll have more friends. So with that, thank you for your attention, and um, this wraps up my presentation. Thank you very much.